Okay, we are bypassing the standard introduction today and jumping straight into something I see all the time. It's a really common fatal exam error. I'm going to show you a trap that 9 out of 10 students fall into, and it quietly costs them their grade. So let's look at this mistake right now before you end up making it yourself. Imagine a student is asked to convert this giant 16-bit binary string, 10111111000101, into hexadecimal. They calculate the whole thing out as one massive denary number, and they write down 48,905. Sounds super impressive, right? Well, actually, it is completely, fundamentally wrong. This exact trap costs students full marks every single year. Section 1. The fatal exam mistake. Section 2. Decoding base 16 logic. So here's what's really going on behind the scenes. Computers, at their absolute core, do not process hexadecimal. Ever. They literally only see binary code, just ones and zeros represented by logic gates switching on and off inside the machine. If you try to calculate that massive binary string as one giant base 10 number, you're completely misinterpreting the core requirement of the syllabus. We use hexadecimal merely to condense those long, error-prone binary strings into something much shorter. It is entirely for human benefit. It just makes it so much easier for programmers to read, debug, and spot careless mistakes without getting totally lost in a sea of ones and zeros. So, how do we actually convert binary to hex the right way? Well, there's a really precise 3-step mechanism you need to know for the mark scheme. First, you take your long binary string and split it into 4-bit groups, and you must always start from the right-hand side. Second, if your final group on the far left doesn't quite have 4 digits, you simply infill with zeros. And third, you assign a specific hexadecimal digit to each of those 4-bit groups. Now, in the hexadecimal system, the digits 0 through 9 are exactly the same as our normal everyday denary system. But because base 16 needs 16 unique characters, we literally run out of numbers. So to fix this, we use the letters A through F to represent 10 through 15. A is 10, B is 11, all the way up to F, which stands for 15. Let's put that method to the test and fix that massive mistake from our cold open. We take our original error, 10111110001001. We split it into 4 distinct blocks of 4. The first block on the left, 1011 equals 11 in denary, which we know is B in hex. The second block, 1111 equals 15, which is F. The third is all zeros, so that just stays a 0. And the final block, 1001, is 9. Put all that together and you get BF09. That right there is the perfect, examiner-approved answer. See? No massive calculations required at all. Section 3. Hardware and System Architecture. So where do these hexadecimal values actually live physically? Well, they're stored in temporary memory components right inside the CPU called registers. To score well on exam questions about this, you really can't just give a memorized definition. You have to build your answer in layers. Start with a simple explanation of the register's core purpose, then add the correct technical vocabulary, and finally shape it into a response that connects the register's function directly to a specific real-world scenario. And when those hex values need to move around, they travel across system buses. But a huge trap students fall into here is just rattling off generic facts. For example, if a question asks about data transfer in a hospital network, you cannot just list floating definitions of buses. You absolutely must tie your answers specifically to that context, explaining the step-by-step mechanism and justifying exactly why a specific data transfer method is better for that particular hospital system. You know, examiners absolutely love trying to trip you up on frequently confused ideas, like the difference between memory and storage. Memory is temporary, while storage is permanent. You can avoid getting confused by asking yourself 4 simple self-check questions. What is it? How does it work? Where is it used? And why is it better or worse? Doing that ensures your answer is fully fleshed out and basically impossible to penalize. Section 4. Networks, security, and algorithms. Let's talk about algorithms for a second. Think of them as a precise logical blueprint. Before any data, like those hex strings we converted earlier, is ever transferred across a network, an algorithm calculates a checksum value. Then, the receiving device reruns that exact same algorithm. If the checksums match, boom, the transmission is successful. But if they differ, the receiver knows something went wrong and requests retransmission. This is exactly how networks manage to catch errors in data streams. Now, when we're talking about securing all that data transfer over the web, the crucial difference you need to understand is HTTP versus HTTPS. HTTP sends data in plain text, making it vulnerable, while HTTPS actively encrypts that data using SSL or TLS protocols. To master this topic, you have to really rehearse your reasoning. You must be able to confidently justify why encryption secures our data across the web, instead of just saying something vague like, a padlock icon appears in the browser window. And speaking of security, when you're dealing with internet risks, a super common error is giving context-free facts. You really need to identify what the question actually wants. Is it asking about physical security, like a locked server room? Or is it asking about logical security, like a software password? Once you classify it, you then have to explain the exact sequence of how it protects the specific scenario they gave you, like a bank's database, for example.
Section 5, the Interactive Knowledge Challenge.
All right, quick challenge time. Let's see if you can spot the error in this statement. Computers process data in hexadecimal because it is faster than binary. You have 10 seconds to spot the fatal flaw in this exam answer before the red pen reveals the truth. Think back to our very first principle from today's explainer. Okay, time's up. Did you catch it? If you did, you're thinking exactly like an examiner. Computers never, ever process hex to gain speed. That is a total myth. The mark scheme-approved reality is that computers only use binary code. Hexadecimal is strictly a visual overlay. It's used to shorten long binary strings, entirely for human benefit, making it so much easier for us to read and manage data without making careless mistakes.
Section 6, Final Recap and Takeaways.
Let's wrap this up. If you lock these 4 things into your brain, you are going to instantly bypass the traps that catch most students. Number 1. Always split binary into 4-bit groups starting from the right. Number 2, remember your hex alphabet, A equals 10 through F equals 15. Number 3, build your hardware answers in layers to ensure deep technical responses. And number 4, always anchor your explanation directly to the specific scenario given in the prompt. If this explainer helped these complex concepts finally click for you, make sure to follow this exact advice. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've covered a ton today. You know how to flawlessly convert hex, you know how it travels on system buses, and how algorithms check it for errors. But I want to leave you with one final provocative thought. You now know exactly how this data is formatted and moved. But what happens when a hacker actively intercepts those exact hexadecimal packets on an unsecured network? How do we actually stop them? Well, that opens up an entirely new layer of logic, and it's exactly what we'll be uncovering in our next explainer on cybersecurity protocols. Keep learning, and I'll catch you there.